here for is, I want to record it, it's Fred. We're on antenna design case study. So I'm looking forward to this myself. I know we all are. So I've opened up the screen sharing for yourself, Fred. I'll mute everybody if that's okay. And then you can unmute yourself. Is that all right, Fred?
Yeah, that's all right, of course.
Yeah, right. Over to you, Fred.
Okay, I'm going to start by sharing some screen. Today, we're going to talk about antenna design. Oh, by the way, so if someone has a question, it's okay to interrupt me. If someone, I cannot see the chat right now. So if someone has a question through the chat, if someone can tell me, you know, just give me the question and I can answer that question. It's so, I mean, it's okay to interrupt me during the presentation. I have no problem with that. Who am I? I am Fred W6BSD. I work all my life in software, computer software. I work building, lately for the last 15 years, I work on building clouds. And I am fairly new in ham radio. I got my license. I got the 3 levels in the US: a technician, general, and extra in 2 months. And so when I got my general license, the first thing I did is I went to the candy store. I bought a radio, and I bought the cheapest feed line I could find, and I bought the smallest antenna I could find also at that candy store. I didn't want to, I thought I don't want to be like those crazy people with giant antenna on their roof. So I want to have something discreet. And then I start to, I could hear people, and I tried to contact them, and I couldn't contact them. The first contact I did was a guy that was 3 streets down from where I live. And then I thought, okay, I need to figure out that, those antenna, how they work, and how to, how to have something that is more efficient than I had at that time. And I spent the last, 4 or 5 years studying antenna and trying to, understand how the antenna are working. So the goal for tonight. So tonight we're going to design an efficient antenna and feed line. So I am always, when I talk to people on clubs here or to new AMs coming to the hobby, I said, I talk about antenna system, because an antenna without the feed line, it's, it doesn't work without a feed line. It's like before we were talking about cars. It's like, focusing on, talking about the engine and talking about the wheels, and never talking about the transmission. The antenna, the feed line is that transmission line that's going to transfer the power from the engine to the wheel. And if you have, and I think in mechanic, we said the same thing. The impedances need to match in order to achieve the maximum transfer of power. And in the radio is the same thing. So that's why I don't like to dissociate feed line and the antenna. So I hope tonight we're going to learn a few things and we're going to have fun. So but before we start, can someone tell me what's wrong with that mast? No one?
Oh, it's bent. Know that.
Yeah, it's not because of the wind. So before modeling software, so that mast is a site in near San Diego. I mean, it was a site near San Diego. It was a Navy site where they were doing antenna testing. So basically, if you can you guys see my mouse on the screen?
Yes, we can. Yes.
Okay, cool. So here you see that's probably a scaled down model of a Navy ship, and they are the transmitter, they are the antenna, and they are the receiver. If you follow my mouse, at the base of the tower, and they were transmitting. And that ship was on some kind of lazy Susan. They were rotating the ship for 5 degrees and transmitting and, you know, writing the numbers on the receiving side. And they were doing that until the ship had done, you know, 360 degrees. And then they were moving the receiver up the mast and doing that again and up and up. And once they had all those numbers, they were giving those numbers to a guy with a, you know, probably a white coat and a ruler. And the guy was drawing those, you know, those graphs where they represent the far field. So now we don't have to do that, fortunately. We can use, you know, antenna modeling software. So for the exercise tonight, we're gonna create an antenna for a fictional winter field day. So there is a team here in California. They want to run field day, and to work field day, they have a strategy. And the strategy they have is they're going to put a G5RV in the tree. The G5RV will allow them to work, you know, all the bands from 80 to let's say 10 meters. That's to accumulate as many bonus as possible by working as many bands as possible. But in California, most of the points you are making during those events are on 20 meter and with people that are on the East Coast. And between the East Coast and California and the Pacific Coast, there is a big blob of nothingness in the middle. You have, you know, a bunch of states where you have, you know, barely anyone. So their strategy is to build a quarter wave vertical antenna. So with a low takeoff angle, so like that, they can, you know, more easily work the East Coast on 20 meter. So they want to work that quarter wave because they're easy to deploy and take down. They're, you know, easy to design, they're easy to build. They have a good takeoff angle, like I said before, and also that's a good set of problem for, you know, our presentation tonight. So now we're going to build the antenna. I'm going to switch application. I'm going to unshare that screen. And I'm going to share different. Okay, can you see the new application I'm sharing?
Yes, we can see.
Yes, can see that.
Okay, so the goal for you is to follow my mouse because I'm going to go pretty fast. And if I'm going too fast, just you know, say stop and go back, or you know, ask me questions. Like I said, there is no problem doing that. So we're going to design that vertical quarter wave antenna. It's pretty simple antenna to design. So I'm going to grab my, you know, drawing tool, and I'm going to draw my. I'm going to zoom in a little bit. And I'm going to draw my vertical antenna. So I'm putting you know, in the middle of the graph, I'm putting my 5 meter long antenna. So I didn't do any math. The only math I did is, you know, take 20 meter band divided by 4, and I have my 5 meters. I didn't take anything into account like the velocity factor or all those things. That's all I'm doing. So here I am. I have my antenna. As you can see the numbers here, I am in the middle of my plane. The antenna is 5 meters long, and we're going to build that antenna not off of a wire. We're going to use something cheap that is everywhere here in the US. That is a chain link fence railing. It's a piece of you know, pipe that is a 1 inch and 3/8, I think. So it corresponds roughly to 35 millimeter. And it's that railing is it's not aluminum or things like that. It's just iron. So I have the 3D view of my antenna here. As you can see, I am going to choose a feed point for my antenna. So I'm going to choose the beginning of the wire. So here's my antenna. At the bottom here, the circle represents the feed point. And we're done. We have our antenna. So let's see now how that antenna is behaving. So I'm transmitting on 20 meters, you know, 1415, for example. I know in Manchester you have a perfect ground, but not everyone is from Manchester. So I'm going to use a real ground. So the dielectric for the ground is 1350. It corresponds to an average ground. Nothing exceptional, nothing too bad. It's just, you know, average ground. Since we have a quarter wave ground-mounted antenna, we're going to put radials. I think 8 radials during the field day is easy to deploy. It's not too little, it's not too much. I mean, I think it's a good number, but we can, change that if you want. So like I said, the antenna is ground mounted, so it's at 0 meter from the from ground, and we're going to use we could use a aluminum pipe, but we want to build something cheap, so we're going to use iron piping and see how that antenna is behaving. So here's my my numbers. My takeoff angle is 27 degrees, so I have a pretty low takeoff angle. That was the goal of that, for that field day. They wanted to have a low takeoff angle to work the East Coast. I have an omnidirectional antenna, so I have no front to back ratio. I have no gain. My SWR is 1.328. It's because the impedance of my antenna is 36 ohm. So a lot of people, they think an antenna should be 50 ohm, but that's really rare. An antenna, when you have 50 ohm, is either because someone did something to that antenna, or it's because there is something wrong most of the time. But here we have a 36 ohm, which correspond, roughly to normal impedance for a vertical antenna that gives us a SWR of 1.328. But right now, I'm not really focusing on those numbers. I kind of don't care about those numbers. Let's see at the far field. So that's typical far field for a vertical antenna. So the graph on the right here is me standing next to the antenna, looking at the antenna. The antenna is vertical here, and that's my radiation pattern. And I have a 27 degree radiation takeoff angle. That means the signal at 27 degrees, that's where the signal is the strongest. If I look at the graph on the left, that's an omnidirectional antenna. So my antenna is in the middle. I am flying over the antenna, looking down at the antenna, and I see a nice 360 degree radiation pattern. I can see the 3D one where I see my donut shape radiation pattern. Okay, so now we have an antenna for field day. But you have Chris. Someone comes to me and say, "Hey, Fred, look, here's California or San Francisco. The East Coast is here. We are sending all that signal on the East Coast, which is good, but we're also wasting all that signal toward the Pacific. So can we do something about that?" Say, okay, let's look at our antenna. So maybe if we we take that antenna and we put on the back of that antenna, if we put one more pipe, it's going to act like a reflector. Maybe we can send more signal toward the East Coast. Okay, so let's try that and see how things are working. So same thing, I'm not doing any math here. I just took 5 meters on the back of the antenna. It corresponds to a quarter wave. I'm putting a -5 meters, and I'm putting one more element that's 5 meters long, and just try to see what we are getting. So I'm going to start again, and I'm getting 24 degrees. So I have a better lower takeoff angle. I have now a front to back ratio, meaning my antenna is not omnidirectional anymore. So I have a directional antenna. I still don't know which direction, but I have a directional antenna. My total gain is a 4.7 dBi, and my SWR is a little bit worse because of the impedance went down. But that's fine. I'm not focusing on that right now. Let's see the far field. Here's my new radiation pattern. So you see a big lobe on the front, a smaller lobe on the back, and now I am sending less signal towards the Pacific. So that's cool. So if you look at the antenna, it kind of start to look like a Yagi, with the driving element here, with the reflector. So if we put one more element here, it's gonna maybe we're going to improve this, the signal strength toward the East Coast. So let's try that to see how things are working. So 5 meters away in the front, 5 meters, I am putting one more pipe, and let's see. Well, that's our antenna, and let's see what are the numbers. So now I have a 90 degree elevation angle, pretty good. It's lower than before. but there is a problem because I lost my front to back ratio. And I have a 5 dB gain, total gain of that antenna. So I'm still, having some gain, but I lost my front to back ratio, and my SWR went crazy here. So let's see why I lost my front to back ratio by looking at the far field. So here, my antenna is radiating equally in both directions. So that's the problem. So if I look at the antenna, it's because all the elements are the same, have the same length. So if I look at the 3D here, you see my radiation pattern is the same on both of those elements of my antenna. So maybe it's because I don't know if you look at the TV antenna on the roof of a house, for example, you're going to notice that the element on the back is always a little bit longer and the one on the front is a little bit shorter. So maybe that's why I'm having problems right now. So the only thing I'm going to do is I'm going to put the one on the back a little bit longer, and the one on the front a little bit shorter. Okay, let's see, what do we have right now? So now we have, okay, 20-degree elevation angle, still pretty good. We got our front to back ratio back. We have a 6.5 or 6.6 dB gain, which is better than before. And we have a total gain of almost 7, which is also better than before. And our SWR is a little bit less crazy. So let's see how things are working. So here I have my new radiation pattern. We can see the 3D, which where we have a smaller lobe on the back and a bigger lobe on the front. So now the people doing that field day, so we can continue fiddle around with that software, but they need to make a decision. So the decision they need to make is, are they going to build the 3-element antenna, or are they going to build the 2-element antenna? So I'm going to compare the 2 antennas, and here I have the radiation pattern for those 2 antennas that we can compare. So I'm going to put one on blue, so it's going to be easier here. So the 3-element is the blue one, and the 2-element is the red one. So I have a question for you guys now. Which one do you think the club, those people, should build, the 3-element or the 2-element?
The 3-element's got more gain, and that'll go for.
Okay. Is it always good to have more gain?
Well, you'll go further with more gain. 6 dBs of gain is double the range line of sight.
Okay, so but the other one has 5 dB.8. So it's not just the double compared to the 5. It's a little bit more gain. So, but well,
if I one isn't quite as directional, is it? It covers more ground.
Sorry, can you repeat that?
Yeah, the 2-element one isn't quite as directional. So in fact, it's
that's what I was about to say.
Greater area for the signal.
That's what I was about to say. So there is a, on when you build an antenna, there is no free lunch. If you're gaining something somewhere, you're losing something somewhere. So you need to always take those into consideration depending on what you want to do. So for that field day, if I had to build that antenna, I would build the 2 elements for 3 reasons. So first of all, it's something that needs to be deployed quickly. So 2 elements are going to be easier to deploy and faster to deploy than 3 elements, especially not just putting the stake on the ground. It's just tuning that thing, making sure the antenna is working the way it's supposed to do. So 2 elements are going to be, I think, easier. Also, the second reason is the angle, the beam width of that antenna. The 2 antenna has a larger beam width. So I want to contact the East Coast. I want to make contacts with the East Coast, but don't forget there is Canada here. there is here I have Los Angeles and Arizona and New Mexico, somewhere around here, where I still need to make some contacts. I will, make some contacts on those areas. So having an antenna with a wider bandwidth will, I think, help me in those conditions. Having an antenna that is two directional, since it's it's vertical, there is no rotator in that antenna. So I won't be able to say, oh, there is a guy in Canada that I have a hard time, so let's rotate the antenna. So that antenna is going to be fixed. So I think a large beam width will, I think, will help. And the third thing is the 3-element antenna will have a narrower bandwidth than the 2-element antenna. So having a wider bandwidth also, I think, will help me, because the 3-element, I will have to choose if I am tuning that antenna for CW digital or phone. And if I tune that antenna for CW digital, that means I need to have a tuner for phone, and I mean I'm going to have some losses in that on phone, and vice versa. So if I do the tuning of the antenna on phone, then it's going to be lousy on CW and digital. So that's why there's trade-off that needs to be considered. So but since but we're going to continue by building the 3-element antenna, because it's more challenging for the rest of the presentation, and it's more interesting, I think. So so since we're continuing with the 3-element now, you look at that radiation pattern. It's kind of ugly. It's not, very beautiful. Also, I didn't do any math on the length or the spacing of the elements. So I need to, maybe, work on that thing a little bit. And I think I can improve those, those numbers here. So the, one of the things I can do, oh yeah, and one last thing is the antenna right now is not resonant. So how do I know that antenna is resonant? Can someone tell me why I can say the antenna is not resonant?
It's the impedance, that's why.
Which impedance?
To be 50 ohm with including the feeder and the antenna to get maximum transfer of power.
It's got some reactance.
Yeah, that's a reactance. So that's what's telling me that the antenna is not resonant, because to have a resonant circuit, I need to have the capacitive reactance and the inductive reactance. They need to cancel each other. So meaning J of X here, I have 21 ohm of reactance. So I need to have 0 here. So right now my reactance is inductive because it's a positive number. So I need to have 0 here. So I want to, fix all those problems. So to fix those problems, so I, improve my gain and fix that resonance, I can do two things. So either I can go on, here and fiddle with those numbers until I find something that is interesting, or I can, ask the software to do that optimization for me. So here's the, the optimization part. So I want to, work a little bit of on my gain. So the cursor allows me to say, okay, I want to, really work hard on the gain, or I want to not work on the gain if I put the cursor on that side, but, it's somewhere in the middle. So I want to have, consider the gain during that optimization. I want to improve my front to back ratio. Elevation, I don't care on the vertical antenna, because I know I'm going to have a good, since it's a vertical, I'm going to have a good elevation angle. I don't care if I have 22 or, a few degrees more or less, it won't change much. I want to work a little bit on the reactance of my antenna. I don't care about the SWR. People are focusing on the SWR. On the antenna, but that's not really the place where you need to focus on the SWR. So the SWR right now, I don't care. And I know, since I'm using a vertical, I will never have a SWR of 1-to-1 without doing something else. So I don't care about the SWR right now. So I'm going to specify what I want to optimize. So I want to optimize, I have 3 elements of my antenna, and I want to optimize all the elements. And if you look here, you see 5 elements. It's because I have my 3 elements that I want to optimize, but also the spacing between those 2 elements for the software, that's also something that can be optimized. And consider that as an element. So let's start the calculation. So you see the software is doing all that, those math to calculate, to reach the goal I gave the software for the optimization. So here, I'm not saving that. I'm going to start calculating again. So now here I have, after all that calculation, I have, 10 dB, almost 10 dB front to back ratio, which is pretty good. My elevation angle is 22 degrees. It's pretty good. 7 dB total gain. And like you see here, I have 483. So my SWR is even worse than before because I had 448, but now my antenna is resonant. So it's because I said before, the impedance of the antenna has nothing to do with the resonant or not, or the SWR is linked to those things, but it's not because I have a one-to-one SWR that my antenna is going to be resonant at that frequency. So now I have, let's see, the new far field. So here is I have something that is a little bit better than before. I have a smaller back lobe. I have a bigger front lobe. If I look at my takeoff angle, it goes from 41 degrees. So it's pretty flat to maybe 9 degrees, 8 degrees. So I have a pretty flat, well, I think I'm going to have a pretty efficient antenna to work the east coast of the US. So now if we want to build that, I think we can build that antenna because we have something, if you look at the numbers here, it's a pretty good antenna we have here. But we have one problem that we need to solve is the, how we're going to transfer the power, the maximum, achieve the maximum transfer of power to that antenna with those numbers here. So to do that, I'm going to use a different software. So, but before I switch software, is there any questions?
What's the software done to the actual physical dimensions of your aerial, Fred?
Yeah, sorry, I can show you that. I forgot to show you those things.
Yeah, just interested to see where it ended up.
So I'm going to share that.
How can we get a copy of the software?
It's free, you can download it. I'm going to give you the URL at the end. So here's my new dimensions. So the driving element, instead of being 5 meters, is 485. The reflector is 5 meters 13, and the front, the one on the front is 4.7 meters. And if you look here, the spacing also changed. The one on the back is at 4.6 meters, and the one on the front is at 4.7 meters.
Okay, thank you. Interesting.
Yeah, no problem. Any other questions? Okay, I'm going to continue. So now, we have, I wrote the number. So we have a 10 ohm impedance on our antenna. So we need to figure out how we're going to, do a matching for that antenna so we can have the maximum power transfer of power. So for that, I'm going to use a software that is called Smith. So basically, it's a Smith chart software. So I guess you all know what is a Smith chart, but as a reminder, so a Smith chart is a way to plot your antenna on the graph like the one you have here on the right. So everything that is on that line in the middle is going to be a pure resistance. So here, for example, is 50 ohm resistance. Here's 25, here's 10 ohm, and everything that's going to be, every time you're going to have your antenna above that line is going to be inductive, and every time it's going to be on the bottom of the line is going to be capacitive. So here, if you look at the blue point where I have my mouse, now I have an antenna that is 25 ohm and is purely resistive. So the goal of that software is take that point and bring it here in the middle. So 50 ohm and purely resistive. So to do that, I can use a resistor, which is, well, it's a bad idea. I can use a transformer, which is a better idea. But the best way it's going to be to create a matching network. So use a series inductor or shunt inductor or series and shunt capacitor to kind of move that point here. So here in that example, for example, here what I can do is to use a series inductor to move my point here, and then use a shunt capacitor to move that point here. So that's how, basically it's like a game. It's how the thing will work. So we're going to use that software. And that software, on top of that, is going to give us a lot of information like power transfer. It's going to do a lot of math for us. So the Smith chart is some tool. So you can do that, with pure math. It's going to be very, very math intensive. You can do that by using a Smith chart on paper. On the paper is going to help you, but you're still going to have to do some math. Here, there is no math to do. So it's super easy to do a machine network using a software like that. So let's start. So let's start with the new circuit. If you look here, what I have is I have my generator, which is my radio, anything that generates a signal. It can be a signal generator, a radio, it can be an antenna analyzer. So that's what's generated my signal. So I'm going to put the frequency for my signal. So I am 20 meter, 1.5, we said before. I have 50 ohm impedance, and now let's say I'm transmitting with 100 watt. On that side here, you have the load. The load is the antenna. In our case, it's the antenna. So now I have a magic antenna because my antenna is 50 ohm and is purely resistive. Okay. So for that field day, let's say I need to, bring that power to my antenna. So I'm going to use a feed line. I'm going to use, for example, RG8X because it's, one of the popular, cheap, popular feed line. And let's say I'm going to use a 75 foot of that field line. So now the thing that is very important, my radio with that magic antenna, my radio is seeing 1-to-1 SWR, perfect. I am transmitting 100 watt into that power line, and on the antenna is going to radiate 82.63, 82.63 watt. So that means I have some losses in that cable, and the maximum transfer of power that I can achieve with that magic antenna using that wire is 82 watt. Let me change something here. 5 and so here I can go change the graph, and here you see the SWR with that magic antenna, and you see that transfer of power with that magic antenna. Unfortunately, my antenna is not 50 ohm, it's 10.35. And the reactance is minus 0.07. So it's basically zero. So now with that, with my antenna and using that feed line, the maximum transfer power I can achieve is 46 watts. So I need to improve that. And my SWR at the radio is 3:1. So you see here, I have the plain line is my SWR. I have 3.5 almost, and that's my power here. So I need to improve that. So to improve that, usually what the people are doing is they don't like to see a 3.5 SWR. So usually what they do is they stick an antenna tuner on the back of their radio, and they're happy because they see 1 SWR, 1-to-1 SWR. So they think everything is okay, but in fact they're only transmitting 66 watts. So you remember the maximum power I can achieve with that cable is 82 watts. So I am kind of far away from that 82 watt. So there is something better that we can do. So instead of putting an antenna tuner here, let's build a matching network at the base of the antenna. So for that, like I said before, we can use inductor and capacitor to move that point here, move it here. So what I'm going to do, I'm going to put an inductor, and you see my inductor move that point, that's blue line, all the way up here. So I'm going to change the value to bring my, the antenna on that line here, because then I can follow this line here to go to 50 ohm. So, and to do that, I can use a capacitor and change the value, and I'm bringing my antenna here in the middle. So now what do I have? I have a 1-to-1 SWR, and the power transfer is 81 watts. So meaning I'm pretty close to what I had before. And if I look here, you see I have a 1-to-1 SWR, and I have I'm transmitting 81 watt, almost 82 watts. So I think it's better. That thing is, better than what we can achieve using an antenna tuner. So, but the problem is to build that network, we need to have some information about the component. So one of the first information we need is to know the voltage across that capacitor. So the software is going to give me that. So if you see on that line here where you have the question mark, so I have a volt is 64 volts. So I need to find a capacitor that is capable of handling at least 54 volts. Usually what I do is I take that value and multiply by 2 or 3. So meaning any capacitor that is capable of handling, 250 volt or 500 volt, that's kind of the standard values. They can be, I can use those capacitors. So it's 10 cents maybe for if you buy them, buy one. The value of the capacitor 438.2 picofarad doesn't exist, but 440, that's a value that exists. So I can use that. So next I need to build a coil. So the coil is, you go online, you're going to find a ton of calculators to calculate the number of turns you need for your coil. But the value I need to know is the current that's going to go across that coil. So here the software is giving me 2.8 amps, so meaning 3 amps basically. So 3 amps, I can use a gauge 18 or gauge 16 wire. But what I want is, the coil, if I stretch or compress the coil, that's going to change the value of the coil. So what I want is I have something, a piece of wire that is really stiff, so the thing doesn't risk of being compressed or extended. So that's one of the reasons. The second reason is the Q factor. The quality factor of my coil is going to depend on the internal resistance of that coil, the pure resistance of that coil. So right now I have a Q factor of 200, but if I use a very thick wire like a gauge 10, 8, 6, or even 4, I can increase that Q factor from 200 to 400. So now, if you look at my power transfer, I have less losses in that coil. I'm achieving 82 watt of power transfer using that feed line. So I'm pretty close to what I was capable of achieving before, with the magic antenna. So now I have a good matching network for my antenna. I have a good antenna that is transmitting, all that power. And so the only way I can improve that will be to use a different coax. So RG8X is, the thin coax that is pretty lossy. If I use, not RG8X, but RG8, I'm going to have a better coax and achieve a better power transfer. I'm not even talking about LMR 400. Here in the US, LMR 400 is pretty popular because it's very low lossy cable, but it's pretty expensive. So I'm not going to even go there. I'm going to just choose RG8. So now by using that RG8, here is my transfer power. So I'm achieving 90 watt of power transfer. Is there any question on that? Everyone fall asleep?
No, very interesting program. It's first time I've seen that one, Fred, and very interested in that program. Yeah, so I'll ask you more later on that one.
So I have a bonus on that presentation. If you guys are interested, it's a 5-minute bonus on that, on that software, on the SimSmith software. So if you're interested, I can, continue.
Yes, I'm happy with that.
Okay, I'm going to reshare the screen. So I'm going to show the entire HF band. And I'm going to switch to dB instead of watt. So here's one thing that everyone that went on the field day where you have several stations working at the same time, they all know that problem. So you are here on 20 meter, you are transferring 90 watt of your power to the antenna, you have one-to-one SWR, everything is perfect. but you have sitting next to you on 40 meters, a madman with the CW key banging like a crazy, and it's generating a lot of QRM that is getting into your radio and make it hard for you to understand weak stations. So can we do something about that? So here, people who know those kind of circuit, they will recognize that's a low pass filter. So meaning it won't, you don't have any attenuation on the low frequency, and then you have a nice roll off on the higher frequency. That's not a super efficient low pass filter because it's only 2 components, but it's still a low pass filter. So if we change that and rotate everything, so I'm going to rotate everything and I'm going to retune that thing. So change the values of the capacitor and the inductor. And I'm going to do that quickly. So now I'm still transferring 90 watt, but now I have a high pass filter, meaning you see I have a attenuation of the signal on the lower frequency, and I have no attenuation on the higher frequency. That means the guy on CW here now has almost 10 dB attenuation compared to what I had before. So meaning it's 10 times weaker than what I had before. But I think we can do way better than that. So here, if you look at the, where I have my feed line connected to the radio, if I put an open stub here, and I put that stub, I want to eliminate, 7.1 megahertz, and so I'm putting a 90 degree. I want to have 90 degrees. So meaning now I put 20. I'm going to change to put the same coax, or even better, I can put RG213, which has a very the velocity factor is low on 213, so meaning I can use a shorter cable. So now what do I have? So I put a stub 90 degrees. So the software is calculating the length for me at 7 megahertz. So meaning I'm going to attenuate the signal on 7 megahertz, and 22 feet of stub. Now look, I am still transmitting 89 watts, so I lost 1 watt by using that stub now. But the signal on 40 meters has been attenuated. The attenuation is 20 dB because that's where we started it from. So 20 plus 25 minus 45 dB attenuation. So meaning, minus 40 dB, that means the attenuation on the QRM coming from my 40 meter buddy it's 10,000 times weaker than what I had before. So it's a good way to use stub, and it's very easy to calculate those stub using that software to put a stub here and attenuate that signal, and increase my working conditions on my 20 meter band. That's my the bonus on how to feeding that antenna. Any questions?
I was wondering what's actually happening when the software is the software choosing the value of the inductance and the capacitor?
No.
When all the numbers were moving, or are you doing that?
So when I use the mouse here for the capacitor and the inductor, I am the one doing that. So I don't know if you noticed, but I have my mouse on the number, and I was using the wheel on my mouse to increase or increase or lower the value, and then I was just looking at this on the Smith chart to see how long I wanted to have my curve and how long it needed to be to put that in the center.
Right, thank you. Yeah, I didn't realize you were adjusting the wheel. Yeah.
Yeah, I was adjusting the wheel. And the thing is, the good thing with that software is all that math is doing is it's because I have don't know if you noticed, but there is a list of, a very extensive list of wires, and all the characteristics of those wires there, in a wire on that list contain all the characteristics. So the impedance of the wire, the velocity factor, the capacitance, all those values there in the software. So meaning that's why it could do all those calculations for me.
Thank you. Got it.
But I have a question, if I may.
Yeah, go ahead.
When I'm wanting to match antennas, I tend to use series section transformers. That is, different lengths of coax of different characteristic impedance, normally RG 59 and 58. And I normally work out the lengths by doing the actual calculations using the formulae, which is a bit cumbersome. Are you aware of any software that can actually do that for you?
That can do that for you.
Really? Oh, okay. That's useful to know.
I can do that right now. It's really super easy to do those kind of things. So let me share the software again. Share. So let's try new circuit. No. Here's I build a dipole, and a dipole. Let's say I have it's here. So I have that I build a dipole. So I made my dipole resonant. And my dipole is 95 ohm right now. So if you look at the mouse here, I have the impedance of my dipole is the 95 and J is 0.48. So basically it's resonant. So now I want to match 50 ohm. So I get a piece of coax and I put TV cable, RG6, for example. Okay. And now I go to here fit. And what I do is I just, use the wheel and here. So if I use 20 foot of that 75 ohm, I can bring my impedance from here to here. So meaning now I have a 1.2 SWR. And my power transfer, so let's say I put in a 50 ohm coax, I'm going to use the same coax, and I have a the antenna is on at the very end of my backyard. So I have 100 foot of that coax. So now I know exactly how much power I'm transferring to an antenna is 77 watt. And my SWR at the radio is going to be 1 to 1. Does that answer your question?
Yes, it does. That's really useful. Of course, the problem with using series section transformers is that there's a range of impedance values you can match depending on what two characteristic impedances you use. And normally when I've tried to count, I've gone into all the maths and I've been using quadratic formulas and all that sort of stuff. That software makes it a lot easier. Thank you. That's very useful.
So the thing is, sometimes I do, when I do testings or play with antenna, what I do is I use pieces of coax to, let me share the screen again. Sorry about that. Can you see the screen or not?
Yeah. Yes.
Yep.
Okay. So I'm going to remove that. So let's say I have an antenna that, it's here. Okay. So I want to bring to 50 ohm. So I'm going to use a piece of coax. And I am going to bring that, my antenna here. Okay. On that point. And then here, what I can do is I can use a capacitor. Oops. No, sorry. Can use an inductor to bring, my point here. And then I can, put my piece of 100 foot coax.
Yep.
So, but the problem is that thing is pretty lossy. So if I look at here, I'm losing 1.5 watt.
Yep.
If I use the capacitor here, I'm going to lose less than using a piece of coax. So usually I try to avoid using transformers, or I try to avoid using piece of coax to do those kind of things. I rather use a capacitor or an inductor because it's going to be less lossy. It's going to be a little bit more complex to build, but it's going to be less lossy than using pieces of coax. And that's fine because my piece of coax here is it's 40 feet. But sometime, especially on 80 meters, you can have very, very long run of coax like that on the low frequency. And the longer the coax is going to be, the more lossy it's going to be, and also the more frequency you're going to have, the more lossy your coax is going to be. So that's why I try to avoid doing matching using coax. But that's cheap. That's easy to do when you have a software like that. Otherwise, you need to do all the math, and it's kind of a pain.
Yeah, it is a pain. I agree with you. A real pain. Yeah, thank you.
So the goal of that presentation is for people who know what they're doing, like you know what you want to do. So to show you that that thing can be done easily, and sometimes people who know it, they have done that 500 times in their life. They're kind of tired. They want to have the easy way, so they put a very low loss coax. And they put an antenna tuner on the back of the radio, and they, whatever. Okay, I'm losing a ton of power, but I don't care. So I'm trying to show that you can, using software, you don't have to go through all that math anymore. You can pretty easily do that. And so when you know what you're doing, also you can test hypotheses, like I did with the antenna. Let's see, how it worked when I put an element here. How things are changed. How my, radiation pattern is going to change. And here's the same things. Or if I put my matching network here, or if I use that coax, what kind of power transfer can I achieve? Or maybe I should, sometime a transformer is going to be better than using a matching network. So you can, do those testing and see how things are changing, and what kind of power transfer or antenna pattern you can expect by doing that. And the people who don't know those things, I think it's a good way for them to learn, because they just throw things random on the screen and say, oh, that doesn't work, oh, that's lousy, or I thought that would work and it doesn't work. So that's basically how I learn all those things. So by reading article, seeing antenna, seeing things, and say, okay, I'm going to try to model that thing and see what I can expect from that thing, and changing few things here and there, I can see how things are fitting together, and now it helps me to better understand how all those things they tie together.
Can I ask you a question concern? Unfortunately, I didn't get into the meeting till you'd been going for about 20 minutes. But I notice you're using Mana-Gal. Do you use EasyNet as well? And do you have any views as the difference between the two programs?
So I don't use the EasyNet. I use a 4NEC too. Okay. I don't like EasyNet. I don't know why. I cannot get into that software. I use also Cocoa NEC. It's one that is on Mac. So Cocoa NEC, I kind of like it because to define your antenna, it's kind of hard because it's a programming language. So you don't define an antenna by putting number in you can, but it's a programming language. So you have a kind of it's weird to design an antenna by putting a program. But the cool thing with that is you can put, for example, I put my frequency, and the frequency is going to calculate the wavelength, is going to calculate the length of each element, the spacing of the element, all the things. So now I can, design an antenna for 40 meters and have my, see my radiation pattern at, certain height and everything. And I just change the frequency, and now I have a 20-meter antenna, and, without redrawing everything. So that's the thing I like in Cocoa NEC. Mana-Gal, I think it's the easiest to learn. It's easy to design simple antenna. There is some limitations. For example, if you want to draw a G5RV, it's going to be hard because you cannot say, here I have a piece of 400 ohm ladder line or window line. You're going to have to kind of draw that antenna yourself. You're going to have to do some calculation on the spacing and all the things to make sure the impedance match. It's kind of a pain to do that, but anything dipole, simple Yagi, loop antenna, vertical antenna, all those things are super easy to do with Managal. And the thing I like in Managal is the optimization part. It's just pretty simple. You put your elements and it works. One of the things I don't like with Managal is if you want to design, so when you are drawing things, sometimes it's hard to, when you have two wires and you want to connect them together, sometimes it's hard. You have to put the numbers by hand and sometimes it doesn't work. I mean, it's kind of a pain to do that, especially if you have a small antenna, because a small antenna, you have to zoom in a lot. And then, 2 centimeters on the small antenna on 440, for example, can make a lot of difference. And to have, sometimes to have two elements that connect together, it's kind of a pain. That's one of the things I don't like with Managal. But as long as you're working with HF, it's pretty. Oh yeah, one of the things also it's hard to do with Managal is surfaces. So if you want to, let's say you want to see how. So here in the US, the houses they are made with stucco. So stucco, it's a piece of like a concrete stick on the wooden wall by chicken wire. So houses here are very good Faraday cages. So I wanted to model an antenna and see if I was putting that antenna close to my house, how that radiation pattern will be affected. And it was a really giant pain to create that wall surface with the conductor. I had to do meshing. I had to connect all those wires. It took me a long time to do that.
I understand that entirely. I use EasyNet to produce wire meshes, and that's exactly the same problem.
Yeah.
But I'm not sure. I'm not very familiar with Managal. Does Managal have the ability to do near field analysis as well as far field?
Yeah. So if you look at the antenna I was showing before, you see the near field. You see the currents on the antenna. So you're going to see the vertical polarization and also the horizontal polarization of the near field.
Does it give the near field analysis in terms of
numbers like no
electric field and magnetic field intensities?
No, it doesn't do that.
Okay, that's what EasyNet does, and it's very useful, especially when you're starting to look at the implications now placed upon us by Ofcom with regard to the safety of our antennas. That's where EasyNet probably comes in a little bit handy. And the other thing I think I'm correct in saying, correct me if I'm wrong, I think Managal is based upon MiniNEC as its engine, whereas EasyNEC is based upon NEC2. And I think that because of that, when you start using verticals that are near to the ground or on the ground, then I think there are some limitations with regard to a MiniNEC based piece of software like Managal compared to EasyNEC, which is using NEC2, which is a little bit more capable, although it has its own problems as well.
Yeah, like I said before, there is no universal solution that works well on all the cases. There is some limitation on Managal. One of the cool thing of Managal, it comes with a system of software called, let me check, I don't remember now, I'm blanking out. It's called GAL-ANA. So for GAL-ANA is for GAL, the software analysis. So you can take the files from Managal and put that into that software, and it gives you a little bit more information that Managal doesn't give you. So that thing is you need to pay for. So first of all, there's Managal Pro, where it will give you some more information. It's I think it's $90. It's not that expensive. And GAL-ANA, you can use MiniNEC, you can use which I don't remember which one. There is a 3 engine or 4 engine that you can use to do your modeling, different engine. You have a NEC2, NEC4, and MiniNEC 3.
Okay. One final question, if I may, then I'll shut up. I don't want to monopolize it. I'm just interested in the differences between Managal and EasyNeck. Does Managal have the ability to make different sections of the ground have different conductivity and dielectric capabilities, or can you just select the whole ground? Are you able to section the ground into different conductivity values?
No, the ground is going to be so at the beginning you select your your ground characteristic, but you cannot say, okay, half of my ground is going to be a rock, I mean, or some characteristic, and the other the other half is going to be something else.
Yeah.
One of the things that Managal does pretty well, and it's better than, I don't remember which one I had problem with, if it's a Cocoa or neck, or if it's a 4-neck too, is the you cannot have a wire that is long. You need to have sections of wire. And to define those sections, they are pretty sometimes it can be painful. Managal does that automatically for you.
Yeah. Okay, thank you very much. I'm sorry to monopolize the thing, but I use EasyNeck a lot, and I'm not very familiar with Managal. That's very useful. Thank you.
Yeah, no problem. Any other questions?
A lot of the questions I had, Bob's asked, so yeah. But it is taking a lot of the paperwork out of it, isn't it? SimSmith, I've never even heard of that. Is that free, that one, or
everything? Let me share the slides, and you're gonna have the here. Oops. Here you have the URL, and for Managal and SimSmith. I try other softwares, but I have now like I said, Managal is very easy to it's pretty quick to design an antenna and to test something, do a quick test. If you want to have more profound numbers, you may want to switch to something else. But SimSmith is super powerful. It's free software. It's been developed by a guy who's a ham radio operator here in the US. And now that thing is so powerful that it's even used by professional people in the professional world.
I use Managal myself, but I've never heard of that SimSmith. I will make use of that.
The thing I realized, I talked with people who are designing antennas for work, and they don't use any of the software we are using. They're using CAD software, because the problem is to design the antenna. So they're using real CAD software where there is a plugin that use a neck, one of the neck engine on the back. But to design the antenna, they're using real CAD software, because the CAD software is going to give them way more information than what we have here. So here, for example, I can build a beam antenna made of wire. That thing will never stay in the air. People who are building, real antenna for the military or things like that, they need to know how much wind they can support. They need to know, they need to do some mechanical analysis of their antenna. So that's why they're using a CAD software, and those CAD software, they cost a fortune, and they have a plugin on the back that also costs a fortune, but they're not using what we're using basically.
Fred, I have to leave the meeting now, but I'd like to thank you very much for that. It was very, very interesting, and I've learned a lot from you. Thank you very much.
No problem. Thanks for coming to the meeting.
Yeah, it was very good. Thank you.
Thank you very much. Appreciate it.
Yeah.
Thank you, Fred. Can we show? Thanks, sorry.